Hello friends, very good morning. Myself Dr. M. A. Chennaya. Friends, in today's session, we are going to learn a problem on the design of a shaft. Basically, you should know what a shaft is, what are its applications, and how do we select the equations for designing a shaft. Friends, a shaft is a mechanical machine element that is used in transmission of power. So basically, it is a power transmission element. Now, when we say design a shaft, it means to transmit a given power, what should be the diameter of the shaft if it is a solid shaft, or what are the dimensions of the hollow shaft, that is the outside and inside diameter, given the ratio of the outside to inside diameter in the case of a hollow shaft. Friends, here basically while designing a shaft, one should know what are the different types of loads the shaft is subjected to. It could be mere torsion. So we have equation in machine design data handbook which will give you the value of the diameter. There is a separate expression for it or an equation. Similarly, it may be subjected to just bending. So there are equations available in the data handbook. And the most important type of question we come across in case of shafts is the design of shaft which is subjected to combined bending and torsion. So friends, let us start this session with a numerical example on the design of a shaft which is subjected to pure torsion only. Friends, here you can see the question for today's session. Design a steel shaft to transmit a torque of 1500 Newton meter, taking permissible shear stress for the material of the shaft as 60 Newton per mm square. The angle of twist in the shaft is to be limited to 1 degree over a length of 20 times the shaft diameter. And it is also given you the value of G, the modulus of rigidity of the shaft material. Friends, first of all, in the design of any of these shaft, you should first of all find out to what type of load the shaft is subjected to. Friends, here it is clearly stated it is transmitting a torque of 1500 Newton meter. So the shaft is subjected to just torsion only. The torque or torsion is called by other names such as torsional moment, twisting moment, etc. Friends, since the shaft is subjected to a torque, if you just go through the machine design data handbook authored by any author, you will have an equation connecting the diameter of the shaft with the torque and the shear stress. And here, for this case of torque, we have the equation given by MT, the shaft diameter D is equal to 16 by pi into tau ED multiplied by kT MT whole to the power of 1 by 3. Friends, this equation is available in the machine design data handbook. So once you select the proper equation from the data handbook, your 25% of the solution for the question you get. Now friends, let's see what these terms are. Friends, here this D is equal to the diameter of the shaft required as asked in the question, and then we have this term tau VD. Tau VD stands for the permissible shear stress, and this shear stress is given in the question as 60 Newton per mm square. So this is 60 Newton per mm square, which is also called as 60 MPa. So 1 MPa is 1 Newton per millimeter square. Friends, you got this value? Then the value of MT is also given. MT is given as 1500 Newton meter. So generally we convert these to Newton millimeter so that we get the answer for the shaft diameter as so many millimeter. So this is going to be 1500 multiplied by 10 to the power of 3 Newton mm. I have converted the meter to millimeter. So this is a value of. Friend, this KT, there are be two terms called KT and KB. KT and KB are called as shock and endurance factor. So it depends on the type of loading. And in this case, if nothing is specified in the question, you can take the value of KT as 1. That is for a case of steady load. For steady load, it is 1. Friends, we have got all the values required to solve for this capital D. So we substitute the values in this and obtain what is the capital D, the diameter of the shaft required to transmit the given power. So this is equal to 16 divided by pi into tau BD, permissible stress is 60, KT is 1, MT is 1500 multiplied by 10 to the power of 3, and the whole thing raised to the power of 1 by 3. Friends, if you simplify this using the calculator, you get the value of D as 50.31 mm, 31 millimeter. So this is the value of shaft based on the torque capacity. That is, to transmit this torque, this much is the value of shaft diameter required. But in the question, he continues to say that while transmitting this power of 1500 Newton meter, the angle of twist in the shaft, that's represented by theta, should not exceed 1 degree over a length of 20 times shaft dia. Friends, now if you had not asked this part, the solution would have been only this much. But here he says further, the angle of twist while transmitting this torque should not exceed 1 degree over a length of so and so. So we have to find out the value of D again to satisfy the second requirement that the angle of twist is not to exceed 1 degree. So we can say based on torsional rigidity, based on torsional rigidity, we get another value of D given by D is equal to 584 MTL, MT multiplied by L divided by G theta whole to the power of 1 by 4. Friends, once again, I would like to tell you that you need not remember this equation because in this subject machine design, all the information, either the equation or values tabulated are available, and hence these are also available in the machine design data handbook. Friend, what are these terms here? This MT is a torque we know already. So MT is equal to 1500 into 10 to the power of 3 Newton millimeter. Then L stands for the length of the shaft. So this length of the shaft is equal to 20 times the diameter. So 20 times the diameter you have got is 50.31. And if you simplify, friends, this works out to 1060. So we just simplify this equation. So this is 20 into 10 This works out to 1006.2 millimeter is the value of this length. Then we have got, friends, G. G is the modulus of rigidity of the material that is specified, and if not given also, we can take a value of zero point 0.8 into 10 to the power of 3 Newton per millimeter square for steel, and the value of theta is angle of twist that will be specified in the problem. So friends, if you make the substitution here, you get D is equal to 584 into MT 1500 into 10 to the power of 3 into length is 1006.2 divided by G theta. 0.8 into 10 to the power of 3 is G, theta is 1. Everything, the whole quantity raised to the power of 1 by 4. Friends, if you simplify this, you are going to get the value of this D based on torsional rigidity as D equal to 57.81 mm. Friends, this is the value of D required to limit the angle of twist in the shaft to 1 degree. And also based on the torque requirement, you have a value D equal to 50.31 millimeter. So you have got two values. So one based on torsional rigidity, other based on the torque to be transmitted. So friends, then comes the question, which value is to be taken as the shaft diameter, so to transmit the power and also to restrict the angle of twist to 1 degree. Friends, in such cases, the higher of the two values is to be selected as the shaft diameter to sustain and to transmit the given torque. So friends, we are going to take D is equal to R of D is equal to 57.81 millimeter. Friends, this is the minimum shaft diameter required to transmit the given power by limiting the twist to 1 degree. But if this is the shaft diameter required, it has to be turned in the machine shop or you have to get it made to order. But generally, as designers, there is a table in the machine design data handbook which will give the values of standard sizes of the shaft. But as a thumb rule, generally the minimum value of D will be 25 millimeter for power transmission. Then for higher values, like say up to 60, 25 to 60 millimeter, you have standard sizes available in steps of 5 mm. So what's the meaning of that? Suppose I have got 27 millimeter as the shaft diameter required, but we don't go in for 27, take 30. Suppose you have got 37 millimeter, take standard size 40. If it is 42.5, take 45 millimeter as the shaft diameter. And after 60, from 60 to 110 millimeter, it will be generally in steps of 10 mm. Like, suppose you got 68 mm, take 70 as the standard size, 78 mm, take 80 as the standard size, 82 mm, take 90 as the standard size. Like that, beyond this 110, it will be generally in steps of 20 millimeter. Friends, I hope the presentation on this particular numerical problem on this shaft was useful to you. And if you are happy with my presentation, do subscribe to my channel without fail. You share this information with all your friends and relatives doing their engineering degree. Thank you very much, friends.